Hello everyone. In this video, we are going to solve some examples, especially this example about the complex power. Let's take a look at it and let's see what it asks. Okay, this is the given circuit for us, and they said the load is 6 radical 5 VA with this power factor and it is lagging, so it means the load is inductive and the switch is open. So I just consider just part A, we don't have part B, and the reactive power supplied by the source is 24 VAR. So they said find real power supplied by the source, Vs of effective and V load of effective. Okay, we need to find them. Okay, what do we know from this information? So this is apparent power. By looking at the unit, VA means the apparent power. So apparent power of the load is 6 radical 5. And it is VRMS of load times IRMS of load. But we know that the circuit has just they're all in series, so IRMS will be the same for all of the components in the circuit. So I just write it IRMS. So we have also power factor and it is lagging. Okay, so it means that we can draw the power triangle, and this is the angle phi, which means cosine of phi, which is our power factor, equals to 1 over radical 5, which is also radical 5 over 5. So what do we know from this triangle? So why it says also lagging? Since it says lagging, then the reactive power should be positive. So it should be positive. So our triangle should not be in this form. Okay, this is Q, which will be minus, but here it is positive Q. So we need to keep this in mind. Okay, so this is our power triangle, and this side is radical 5, this side is 5. Okay, their ratio. But the apparent power is hypothesis, so it is 6 radical 5. So we got from 5 to this. So what do we need to do? We need to multiply it by radical 5 in the denominator and 6 in the numerator. We need to do the same thing for this one. So it will yield 6. And if we go with Pythagorean theorem, we can find 12 for this side as well. So let me draw the our triangle once again. So this was 12, this was 6, and this was 6 radical 5. Okay, so we know everything about our load. So complex power of the load will be 6 plus J 12. Okay, this is extremely important that we know. And the question says the reactive power supplied by the source is 24 VAR. So S of source will be P of source, which is real power, plus JQ of source. This Q of source is 24. And we know that Q of source is simply equal to Q of load plus Q of line, right? Sorry. Okay, this is our line. And Q of line is simply, from the formula that we know, is IRMS squared times the reactance. What is the reactance? It is 3/4. So okay. So Q of line we don't know, but Q of load we got this, which is 12. So this is 12, and this is also given is 24. So Q of line should be 12 because of the power, conservation of power. So this is also 12. So from here, IRMS, which is very important in this circuit, will be squared will be 16. So IRMS will be 4 amp RMS. We found this. Okay. Now, what to do next? We want to find the real power supplied by the source. How we can find that one as well? Okay, we know the real power of the load, which is 6. And we also want to find the real power of line. So we can write it as, again, I squared RMS times, this time the resistance, not the reactance, 1/4, which will give us, this was 416, then it will be 4 watts. We found this. Okay. So we also know the P of load, which is 6 watts. And again, from here, we can say P of source will be 6 plus 4, which is 10 watts. Okay. Now, we found the first thing that the question asked from us. But what about the effective V of the source and the load? We know that by knowing this information, we can also find the complex power for the source. It will be 10 plus 24J, right? And from here, apparent power of the source will be this expression, right? Just the hypothesis. If we draw the triangle for the source, this is for source, this was for load. Then this part is 10, then this part is 24. So this should be the hypothesis, and we will get what? The hypothesis will yield, let me check it out. It will be 26, I guess. This is 26. Let me check it with the calculator. Yes, it is 26. And this is equal to IRMS times VRMS of the source. We know the IRMS is 4, so VRMS of the source will be 6.5. Okay, so we found also this one, and the last one, the VRMS of the load. What can we say about that? Again, the same procedure for the load. The apparent power of the load will be equal to this expression, which will be radical 180, which will be, we found it, right? It's 6 radical 5. We found it here. We know this, okay? And now, what can we do? and this is also equal to IRMS times VRMS of the load. So this is 4, so from here VRMS of the load is 3/2 radical 5. We found the last thing that the question asks. Okay, in this example also we are given the circuit and they want ask some of the questions, like they want a total complex power delivered to the load. They also gave load 1 and load 2 informations and also RMS value of the current in the source and also the efficiency. Okay, let's solve the part I one by one, and the question is like it is guiding us to get all the answers in order. Okay, so it says the total complex power delivered to the load. We need to find that, and the real power for the load 1 is 1600 watts. So this is 1600 watts, and its power factor is 0.8. So if we, for load 1, we draw the power triangle, and if this is phi, then it will be cosine of phi is 0.8, and the real power, which is this side, is 1600 watts. So from here we can immediately find the apparent power by the cosine, which will be 2000. And this side also, the other side will be can be found by 1800 VAR. Okay. Now, what else do we know? We also know for about the load 2, which has 600 VAR, which is Q of 2, right? So Q of 2 is 600 VAR. And also we know that before the switch is closed, the IRMS value for overall the load 1 and load 2 will be series with the line and also the source. So IRMS is also 30. So what can this mean for us? Also, they gave us 800/9 the efficiency. So from here, efficiency is just P of load, the real power, over P of source, which will be 8/9. This is given in percent, but we got this in 8/9. And the P load, what we can say about the P load? Well, we know that P source is basically P load plus P line. This part, right? This is part line, okay? And P line can be calculated as IRMS, which is 30 squared, then it will be 900 times 1/3, which will be 300. So P line will be 300 watts. If this is 300, then P source, what can we say about the P source? Well, from the efficiency, We know that 300 will be 1/9 of the overall P of source. So in order to find the P load, we should multiply it by 8. So 300 times 8 will be 2400 watts. So the overall load is 2400 watts. The load 1 has 1600 watts, so the remaining part, which is 800 watts, will go to load 2. Okay. We also know for load 1, the reactance power is 1800, and also for load 2 is 600. So the overall, the reactance power of the load will be 1800 plus 600, which will be what? I guess, let me see. It was 1000. Okay, I guess this is incorrect. Sorry about this. If this is 600, then let me check it with the calculator. It will be radical 2000 times 2000 minus 1000. Okay, this will be 1200. Sorry, my bad. And this 600 with this 1200 will be 1800. So this will be 1800 Q of load. So we found I, which is the total power of the load, is 2400 plus J 1800. The effective value of the load voltage, what is it? How can we find the load part? Okay, we know the real power of the load, and we know that the apparent power also of the load. So if this is for load 2, you know, this is 800, this is 600, then obviously this is 1000, right? With the famous ratio. And their apparent power will also sum. Their sum will be 3000. So 3000 will be VL RMS times IRMS. We know IRMS, which is 30, so from here VL RMS will be 100. We found part 2 as well. Also, the question asked about the input impedance Zin. So how can we find the input impedance? Well, we know the formula. Zin times IRMS squared will be equal to this S load, right? 2400 plus J 1800. We know this is 900. So from here, Zin should be 8/3 plus J2. This is also found in part 3. And part 4, the power factor at the load side. How can we find it? Well, we can draw the power triangle for the load. Let's say this is theta, and then this should be 2,400, and this should be 1,800. Also, this should be 3,000. So power factor of the load, which is equal to cosine of theta, which is also equal to 2,400 over 3,000. These zeros will cancel each other, and it will be 0.8. We found this as well. So part 4 is complete. The complex power supplied by the source. Okay, the complex power supplied by the source. Well, the source complex power, which means S of source, is equal to S of line plus S of load. How we can find for the line? Well, for the S of line can be computed as, for the real power will be 30 squared, which will be 900, times 1 over 3, which will be 300, right? We found it previously. And the reactance of the line will be simply 900 times 1, which is 900 VAR. So this is for S line and this is for S load. So if we add them, then the S source, the complex power of the source, will be what? 2,400 plus 300, it will be 2,700 plus 1,800 plus 900. Again, it will be 2,700 J. We also found this part as well. Now let's go to the part B when the switch is closed. Okay, now for the second part B, we are closing the switch, and with this event we are adjusting the source Vs so that the effective value for the V load VL will be the same like in part A. So I wrote it down here, what we found in part A. And then question asks about the capacitance C in different cases. Whenever the efficiency is maximized, also we need to find the efficiency. Also the capacitance C, to find it some way like the power factor load become 12 over 13 and it is lagging. So what to do? Well, we know the information that we got from part A, these power triangle for load 1 and load 2. Now, whenever we're closing this switch, the capacitor will be included in our circuit. But remember, the load 1 and load 2 impedances won't change because the VL effective won't change. But the overall load, which means this overall part will be changed. That's why the V load of the overall load of part A and B will be different because of the capacitance added, and then we will have an extra term in the reactance power because of that capacitor C. So what to do? Well, we for part I, we want to find the capacitance C so that the efficiency is maximized. Whenever we have okay, how can I say? This is the load, inductive load. Okay, so we have a Q plus Q. In order to maximize the efficiency, we need all the power to be real power. So we should not have the component power of the reactance. So we need to have zero reactance power. And for that, we know apparent power for the load will be magnitude of S, load will be radical 2400 squared, plus we know from the previous part we had 1800 reactance power, and as I said, we also, because of the capacitor, we also have another component which is directly have impact on the reactance, so it will be Q of C to the power 2. And this is also equal to VRMS times IRMS. But keep this in mind that VRMS is given, it's because we don't change the VRMS, so it is 100, but IRMS will be changed. It won't be the same as the previous one. So this is not like a substitution theorem. V and I won't change in the magnitude, but their phases, the IRMS will be changed whenever we are going to in the phasor domain circuits. So now, in order to minimize the reactance power, this should go to 0. So in order to that, QC should be minus 1800 VAR. Okay. And so in order to find this, and also we know this source has 50 hertz, so omega will be equal to 2 pi f, which is 100 pi, and the impedance of the capacitor is 1 over j omega c, which will be minus j times 1 over 100 pi. And from here we can say Q of C. Okay, we can say VRMS square over Z conjugate will be equal to the complex power, right? The complex power of the capacitor, and which is equal to minus j 1, since this is Z conjugate, so it should be plus, and right, it should be plus, so it will be 100 pi c, and VRMS square, which is 100 square, which will be 10,000, and this is equal to 1800 1800 J. Okay, now this is also right. This is also minus 1800 J. From here, if we calculate C, we'll get 572.96 microfarads. So we found it. Now in part 2, II, part 2, we want the power factor on the load side to be 12/13. So let's draw the power triangles. So let's say this is theta, and this power factor means cosine of theta, so this part should be 12, 13, and this 5, the very famous ratio. And we know that our power factor, our power triangle, in the real part, in the real power, it won't change because we just added a capacitor. So this part will be still 2400 watts, but the reactance will change. So this part should be 1800 plus Q of C. Okay, this Q of C and the previous one are different. And okay, so the real power won't change, but the reactance and the apparent power will be changed. So what happened? This is multiplied by 200. So this should be also multiplied by 200, which yield to be 1000, right? So from here we get QC equal to minus 800. Please note that the capacitance reactance will always be, the complex of the capacitor will always be negative, and for the inductor it will always be positive. Okay. Again, the same procedure as we did. From here, we know the V effective VRMS squared, so it will be 10,000 over 1 over plus J 1 over 100 pi C, this time equal to minus 800 J. From here, C will be equal to 254.65 microfarads. And this is all for these examples. I hope these examples were helpful. I know they're a little bit complex, but I wanted to show how they can be, these techniques and formulas can be implemented in examples like this, because these examples are very good in order to understand the materials very well. And thanks for watching.